So last week we spent quite some time to discuss about how AES works, and then we went through some details. And so we closed the loop there. So today we are going to cover a slightly different topic. So supposing that we know how AES works, now we are going to discuss how can we utilize AES to, actually encrypt files or messages. So one thing that we've noticed so far was that in AES, the message space is 128 bits, which means that so we would collect, we expect to have a message that is 128 bit. And then once we have that, we can go ahead and encrypt it and probably transmit it on the line. But most of the time, unfortunately, that is not the case. Let me see, there is a noise. Can you guys please mute yourself if you're not muted? Thank you. So the idea is that, in practice, we most of the time would have files that are larger than 128 bits. And the question would be, how do we deal with those kind of messages? Or, let's say you want to encrypt a file, and how can we do that? So one of the idea is that we basically chop the messages into smaller pieces, supposing that this message contains your file, and it is obviously more than 128 bit. One idea is to chop the message into 128 bit parts, and then we use the AES to encrypt that. So let's say this is my message M. So I chop this message into some parts that are 128 bit, and let's say this is the file. I go piece by piece. Take that. Let's say I call this one to be MI. And then what I would do is that I compute for every of these MIs that, the length of MI, let's be very accurate, 128 bits. Given that, then I can use AES encryption, and I can plug in my key and MI, and then I can compute the ciphertext CI, the corresponding ciphertext. So at the end, if I continue over this loop, I can go ahead and compute CI as I have computed on the top, and then piece by piece, 128 bit, I would be able to do this encryption. So basically, what I've done was I chopped my file again into pieces M1 to ML. Let's say I have L pieces, and then I encrypt every piece, which is 128 bits, using the key and compute the corresponding CI. And I put them together, and this would be my corresponding ciphertext that is now encrypted and possibly ready for transmitting it online. So this is one idea. And then the question that we are going to answer today, and we work out on it, is there any other way, or is there a better way that we can combine this, multiple pieces of messages together, so that hopefully we achieve a higher throughput, we achieve, if possible, increase the security if there is any risk over here, and so on and so forth. So that would be the topic that we are going to pretty much cover today. So the idea that we have just discussed now, it is actually a mode of operation. So these mode of operations are very important. So you will hear them a lot on the internet. There are many different, what we call, the way that we will cut the message and combine them together. In this sort of algorithms are called modes of operation. And then if you search on internet, there are quite many different types of them. And today we want to explore some of the famous ones, and do some comparison and see which one is the best for different scenarios. So the first one that we've just discussed the very basic idea, what is called electronic codebook mode, or for short ECB. In this mode of operation, as you can see, I got my message. I chopped the message into L different pieces. So every MI over here is 128 bit. So if you see the notice from now on, we suppose we use AES, but these modes of operations are not restricted to any specific algorithm. You can basically, if there is any algorithm that, let's say, it takes 256 bits of the message space, you can just cut the message into 128 bits. So we are just using, a block called encrypt. We never call it AES. It doesn't have to be AES. So if you basically plug in any other encryption algorithm, just make sure that you cut the message in the right amount, then we are good to go. So what happens is that after we cut the message, we set the keys. So I think the secret design would make it easier to understand. And then our algorithm would take the same key for encrypting every part, and then we would get to encrypt different pieces of messages. So remember, in block cipher, it is okay to use the same key to encrypt multiple messages. That was a stream cipher that we have to change the key, so we don't have that restriction over here, thanks to the design of the block ciphers. Once we've done so, then we get the corresponding pieces of ciphertexts, and after we concatenate them together, we will produce the final ciphertext. So let's begin with a question. What do you guys think about this mode of operation? Do you think this is good? Do you think it has some problems? Anything that really draw your attention? All right, let's say it's given that two pieces of the messages are the same. It happened that your file has some structure, and then some parts would repeat. So if that is the case, then we would say, in this scenario, we suppose that M2 equals to ML minus 1. And let's see what would be the effect of that. So if that is the case, looking into this encryption algorithm, so since we are using the same key for encrypting every block of the message, so with that, what we get is that the C2, which is the encryption of M2 with this key, is going to be equal to CL minus 1, right? Because these two pieces are being, the input messages are the same, the key is the same, so the ciphertext would remain the same. So that would be an issue that we will see an example that how that can affect the security of the system. But other than that, looking into the encryption, so the encryption algorithm, would look like this. We would basically encrypt the different pieces of messages and concatenate them together. And for decryption algorithm, again, we get the ciphertext, we chop it into 128 bits. Supposedly it is AES, and then we would decrypt, all of these pieces with the given key, and then we can recover the message. But this is something that we really need to look into. What will be the impact of this scenario? So I think this is what we are referring to. So, because of the design of this ciphertext, if, let me write it shorthand over here. If MI equals to some, MJ in this, block of messages, then we would have CI is going to be the same as CJ in general. So because of this, most of the file, especially those that are highly structured, it may not be really secure, because, if attacker can look into the ciphertext and knows that, okay, you are maybe sending some document that he knows that it has a structure, or maybe some random message that doesn't have any structure, then this property would help the adversary to distinguish And just because of this repetition, he can tell if you are sending an encryption of that structured document or you're just sending encryption of some random message. So this is something that is bad, and we do not want this to happen. Some may say that what would be the effect of this? So I think this is, a best example. You see this pink one over here. The background is white. And then we have some basic colors. So if we go ahead and we grab, enough pixels, we put the pixels together as a small, squares which contains, 128-bit, 128-bit. And then you can see the corresponding encryption. Even though we have encrypted this file with, AES, which is a strong encryption algorithm. However, you could see that just because the file has repetitive structure, which the background is always white, and you see that it's just like pretty much obvious that there is a background over here, and all of these pieces of messages, blocks of messages, are encrypted into the same ciphertext. The part of the body of the pink one is black, so again it got encrypted into the same block. So I know that this is not quite clear, but it has overwhelming amount of leakage for the adversary, and the adversary can tell that okay, this is indeed a picture of some penguin, for example, or some animal. So this is the case that we really want to avoid. Because of this, today we are going to spend some time and talk about some other modes of encryption, so that it does not come with this restriction. So the very first algorithm that we are going to discuss today is what we call to be CBC, which is called cipher block chaining. So if you see in this example, the second picture that we use it with the CBC, you see that the result has become quite some sort of white noise. So there's no leakage over here, at least from what we can see. So this really perfectly hides the information from the eye of the attacker, versus the first algorithm that you see that is completely leaking a lot of information. So obviously, not always the first and the easiest idea that crossed our mind would be the best option. So this is why today we are going to spend some time over here and explore and see how we can hide the information, the leakage that we've just talked about. So looking into this algorithm, again, we start off with our message. And then we chop our message into different blocks that, every block is, if the encryption method is AES, it has to be 128 bits. And then now going forward, you see that there are some changes. We don't just directly, inject this message into our encryption algorithm and use the key to produce the corresponding ciphertext. There are some changes. So let me begin by the first part. As you can see, in the very beginning of the algorithm, we start with some new variable that it calls initialization vector. Let me call this one in short to be C0, so that, with the rest of this information over here, things would start to make sense. So the idea of this cipher block chaining is that before you send the message to the encryption circuit, you first XOR it with the result of the the ciphertext of the previous block. So let's look into here. If M2 is coming, before we send it to the encryption, we first XOR it with the previous ciphertext that we produce, and then we send that result into the encryption to produce the ciphertext corresponding to this message M2. So since in the beginning we don't have any ciphertext, we would just start with some random value that is called initialization vector. So suppose that we have chosen this initialization vector, and the idea is that we have to choose it randomly for every message. So this is given. Then we start with off, we get the M1, we XOR it with C0, and then we encrypt it. And then that would be our first block, the result of the first, the ciphertext of the first block of the message. Then we go to start with encryption of the second block. So again, as I said, we would take this C1, which is 128-bit, and then we would be able to XOR it with M2, and then we pass the result of that to the encryption, and so that we can produce the C2. And again, to create C3, we would use C2. So again, we use this one as a randomness from the previous part, and then we go ahead and do this sort of encryption. So if now I want to write this idea into some pseudocode, so I'll call it CBC encrypt, that it takes some, key and M. So it's going to be doing this part. So the first thing we want to do is select some random C1. So select C0 to be some random bits of C1 and C2 at random. And then we are going to divide M into M1, M2, M3, all the way to ML. And then now, as you could see, we can write a for loop. So if we can say for I from 1 to L, what we are going to do is we compute CI to be encryption given the key K. So we take MI and then we XOR it with the result of the previous block, which is CI minus 1. Right? And then we will go ahead and produce the corresponding blocks of the ciphertext. So remember that instead of using the name IV, I just rename it as C0 so that it just becomes easier for here, so that we are dealing with this variables. So once we are done with this, so we are just going to return C0, C1, C2, all the way to CL, right? So what you notice is that when we return the encryption, we also include the C0, right? We don't have to protect the C0. We would just, send C0 as a way that, that is our initial randomization. So that when the recipient sees these things, then the recipient would be able to do the decryption correctly using the same initialization vector. So this is like in short how the block this block cipher would work. Any questions so far? Is it clear? All right. So if it is clear, let me ask you this question. So we keep saying that we divide our M into, L different, pieces of messages. What if our block is not divisible by, let's say, 128-bit? That suppose we are using AES, and the last block happened to have less bits. Let's say it has 20 bits. So how can we deal with that? Any ideas?
Can you fill it with noise? Just random values to make it fit?
Yes, so that works, but how can the recipient understand that only 20 bits of the last block is actual information, and the other 108 bits are just noise.
Oh, they can be just the same, like an agreed upon value, right? Because it's not going to show even if it's the same.
Right, yeah. So that means that you have to, feed it out with some random values, and on the top, sending another extra, 128 bits, telling the recipient that, the last from the previous block, 108 bits are random value, right? So just ignore them. Right, again, zero padding. That could work, but again, the same problem. How can the recipient distinguish how many zeros are redundant? How many of them are because of that? So yeah, somebody's suggesting padding with a specific rule. So we have an idea called padding. There are many different versions of this padding, but one of the easiest way that the padding works is, so let me just, oops, what happened? Okay, so let's talk about padding. So what we are talking about is that what if I'm sorry, what if we add a pattern so that we don't have to transfer that extra information that how many bits are actually random. So we say that if the length of the last block ML is less than, supposing that we are working on AES again, 128 bits, right? So we are going to do this one. We are going to concatenate ML. This is the concatenation sign. We concatenate it with 1 and then enough zeros so that the length of this entire thing becomes 128 bits, right? So then we are putting a pattern. So if the recipient received this block ML, then he's gonna start from the end until he finds the first one, and he knows that he has to discard all of those bits because those are not a part of the plaintext, part of the message, and then he would just ignore all of them, right? So now we have a pattern. What if ML ends with 1? So you see that there's no problem. So we start with the end, and then we would go ahead and until we see this 1 and we get rid of it. So if there is any 1 at the end of the ML, we would be untouched, right? So that could be it. And we already had we already added this pattern that it is not random. It doesn't have to be random actually, but it has enough information so that we don't confuse the recipient, right? So the recipient, whenever he sees this piece, then he knows that he has to get rid of enough all the zeros until he gets to this one, and then he's gonna be fine. So do you guys see any other problem over here? Do you think it is fine?
If we don't need the padding and the bits ending is already 1, how do you know do we do the padding or not?
Right, very good one. So that is where I was trying to get into. What if the ML is, perfect and it is already 128 bits? So adding this rule, then the recipient would go ahead and try to remove some bits, which would basically destroy the message because those are not padding. It happened to be, ending with 0 and there's some 1 at somewhere. So how do we deal with that? So since we are adding this idea of padding, so we need to be consistent so that there is no, ambiguity over here. So I'm going to add some part to this code. So else, this else is for the time where ML is actually 128 bits. Okay, this is gonna be covering for that. So the first if it is less than 128 bit, it's not gonna be more than that. And then the second part, we are dealing with the case where it is actually 128 bits. So how do we do that? So in order to deal with that, we are going to add another block, ML plus 1. We are going to let this one to be 1 and all zeros, so that the length of this whole thing becomes 128 bits. So we are just basically adding entire padding to a new block, right? And done. So we already added an extra block over here. So you can imagine that we add another block, ML plus 1. And our algorithm is going to work as before. We would just produce an extra block that happened to be entirely padding. So now when the recipient receive this message, the recipient would know that he has to go and start from the end of the message, remove all the zeros until he sees the first one, and also remove that one, and then he's going to keep the rest of them as the message itself. So in this scenario, the recipient would remove an entire block, and that is just going to be enough for him to know that, okay, no matter if we add padding, we need padding or we don't need padding, there is no, we are already clear, or there is no ambiguity, or for the recipient that whether we have added padding or not, or where our padding starts, when it ends, and so on and so forth. Okay, is that clear? This is obviously one of the ways to deal with this scenario. I'm not saying this is the only way. There are different techniques that people would want to come up with this, but no matter what you want to do, you have to be very clear. So one of the students suggested that we add a random padding at the end of the message, and then once we have added that random padding, we just send another block of a message to informing the recipient that how many of those ending bits from the previous block was padding. Then the advantage of using this scenario versus the other idea is that for our student idea, we always have to send an extra block no matter what, and that block indicates the number of the bits that are noise or padding. But in this scenario, at least whenever we have the last block that has less than 128 bits, then we don't have to transfer an extra extra block of message. It has enough information for the recipient to just remove the padding. The only problem would be when we don't need padding, then we are actually transferring an extra block. So again, that is the only time that we have to transfer that extra block. So it has a little bit more efficiency comparing to the first idea, right? So I hope that this is now clear how we did encryption using the cipher block chaining algorithm. Let's go and see how the decryption works. So we start again on the decryption. Now we want to look at this picture from bottom to top, right? So the ciphertext comes from the bottom, and then we are going to build it up all the way up there so that we recover the message itself. So again, we say that we start with initialization, which we call it C0. We will start to work this out by getting the ciphertext, the piece of ciphertext, which is 128-bit. We send it to the decryption circuit along with the key. We decrypt it, and then we would XOR it with the C0, or the result of the previous block, and that would become M1. Let's see how do we get to M2. So for M2, we get a copy of C1 without even sending to the decryption circuit. So we have it here ready. So we get the C2, we decrypt it, then we XOR it with the previous block, and that would recover us the M2. But let's see if this is actually true. So we say that every time that we produce CI, this is the encryption with the key of MI XOR with CI minus 1, right? According to the construction of our encryption algorithm. So if I want to write the decryption, so the decryption algorithm, given the key, given the CI, we are saying that we define it to be MI, right? This is so when we decrypt this part, we get MI XOR with CI minus 1, right? And then we are going to XOR it again with the previous block, which is CI minus 1, right? According to the XOR definition, these two parts would get canceled, and the result just would become MI, right? So that's why we are taking the previous block and XORing it with the result of the decryption. So then the secret is correct, and the result would be our, what we would have been expecting. So in short, every time that we are going to recover the message MI, we are going to decrypt the corresponding ciphertext and then XOR it with the, the ciphertext from the previous block, and that would be enough for us to get our message. Okay. All right. So let's see. Let's have some discussion to see how and what we've just built. So it is obviously a block cipher. Why is it a block cipher? Because we are encrypting, and decrypting a block of a message, 128-bit, 128-bit. So we didn't change anything yet. So this is like how you would start to see the things that are different. So identical blocks of the plain text encrypted differently, right? So let me go back and let's say I have M1 and M2 are equal to each other. So let's see what happened. M1 would get, randomized with this initialization vector. So we get it XOR, and then we encrypt that one, and it would create the corresponding C1. And then M2, so notice that with this XOR over here, we already changed M1. And then before we send M2 inside, again, we XOR that one with another random variable, right? C1 look like a random variable because AES is a very good encryption algorithm. So he would really hide the message. So the C1 look like some random bits. And we use that randomness to, XOR this M2. And that would add up to this. So they would basically destroy that relationship that M1 and M2 they had together. And then the C2 would become some completely different than C1, right? Do you guys see that? So this chaining effect, and starting with some initial, random value over here, would really correct that issue that we had. That what if some pieces of the messages are the same? Then you can see that using the CBC, just because there's this chaining effect. That could essentially change, those structure of those messages, even though they are repetitive. The corresponding ciphertext, because of combining with different, previous blocks, would perfectly hide those, repetitive structure. So we don't have to be worried about that issue. The next one is actually a very interesting scenario. So a randomized encryption algorithm. So what we have produced so far is actually what we call it a randomized encryption algorithm. So in order to understand this better, let me go back to the construction of our CBC. What happens if I have this message M, and let's say my message M doesn't have any repetitive structure, like there's no piece of over here that are equal, okay? Then you encrypt this file using ECB, and then send it to your, Alice, encrypt this M and send it to Bob. And then later on, Alice wants to encrypt the same file and send it to Bob. So you will see that every time that I encrypt the same message and send it to Bob, no matter if this file has repetitive structure or not, some adversary on the internet, by sniffing the packets, he can see that, oh, okay, Alice is sending a repeated message to Bob again. You can tell, right? Even though there's no structure, but I can see that the entire ciphertext is equal to some ciphertext that he saw before. And that is leaking some information. So you can go through many different scenarios. Let's say you have one file and then you send it to your friend and then you want to send it over, but you don't want anyone to know that you have transferred the very same file. So if that is the case, then CBC becomes very handy. The idea of the CBC is that every time that you send the same message or different messages, let's say for now our focus is the same message. Every time you want to send the same message, because you have to select a random CI, C0, so in the very beginning, you start to make a significant change on the first block, and then that would make a significant change on C1, and that would be like a sort of effect on every other ciphertext that you produce in the future. So even a little bit of change on C0 can entirely change, the result of the ciphertext that you're producing. So this is why we are saying that, this has turned into a randomized algorithm. A randomized algorithm is an algorithm that always takes some input as random, and that would determine, the way that the algorithm works in theory. So what you see over here is that we have exactly the same effect. Choosing the C0 at random would really help us to make sure that every time that we do, even though we encrypt the same message, the resulting ciphertext would look very different and to the eyes of the attacker, and he can tell that we are whether sending the same message or this is a different message. All the adversary can tell is that we are sending messages of the same length, right? We haven't hide the length yet. Any message that you have 128 megabytes, you chop it, you encrypt it, even after padding, it would have the same effect, So that is hiding. The length of a message is a different scenario that we haven't discussed here yet. So this is a very good property that we achieve using the CBC. So I really want to, draw your attention to this part. In the construction of the CBC, or most of this, operation modes that we use randomized input. According to the construction of the algorithm, these inputs, most of the time, they need to be random. It doesn't need to be unpredictable for some algorithms. For some, it also has to be unpredictable, which means that you really have to choose C0 carefully, and it has to be very random. I think the CBC is one of the cases. If you don't do that, if you can, I think there are some proof that show that somebody can break them. But that is not the point yet. The point is in the standardization of these techniques. They use awkward and I would say ambiguous name of initialization vector. Because when you talk about it with a lot of developers, when you talk about initializing a variable, they think that it doesn't really matter. They can initialize it with 0. But as you could see over here, it is not really the case. We really want this initialization vector to be random as possible. So now that you're taking the cryptography course and you understand the effect if you choose the same. If we were to choose the same initialization vector, let's say you initialize it to be all 0 bits, then then we won't have this nice property. If you encrypt the same file, your ciphertext would always remain the same because initialization vector, you don't change it, right? So unfortunately, I don't know why in standardizing the AES and its mode of operation, the committee that they came up with this name, everybody agreed. Those important things that I think you should keep an eye that in future, every time you want to use this sort of algorithms, now you know that this is a sort of misleading definition, I would say. You want always to work with some random values over here, okay? So the next thing we want to discuss is that, so what if there is, we are transferring this C, ciphertext C on the internet, and no matter how good and, non-noisy channel that we have, and we use the CBC codes, to error correcting codes to protect the bits. And if there is any error, we can correct them. No matter what, sometimes error happen. And when error happens, suppose that some of the bits in some ciphertext CI flip, and there are so many of them that somehow the recipient cannot tell that they have changed, even though we use CRC. We have limitation on the number of the bits that we can detect. So now our question is that, suppose that happened, then how many blocks of message we are going to miss? So let's go back to the decryption and see what do we mean. Suppose that some bits over C1 are corrupted or flipped, and for some reason the recipient doesn't detect that. And we want to understand what is the effect of that. So how many blocks of messages would go wrong? So some bits over here are flipped. So when we do, and we suppose that C0 is correct, okay? So C1 is affected, therefore the M1 would be also affected. So of course we would miss some of the bits of 1, or at least we would get them wrong. Since C1 also has to do with the decryption of M2, well, unfortunately that also affects some of the bits of M2. And then let's see what happened to the next one. So let's suppose it is M3. So the C2 is correct. I mean, we can decrypt this one now. It's fine. It only affects M2. But for decrypting the C3, we only use C2. And we said that C2 is correct. Only C1 is affected. So therefore, M3 could recover correctly, and so on and so forth. So that is why we are saying that a transmission bit error in CI always affect the correctness of that block and the neighborhood block, okay? And then after that, this algorithm has a property called self-synchronization, that with this property, once an error happens, then our algorithm would be able to, recover. And as we said, after from M3 on, we would get the correct messages. This transmission bit error on C1 only affected 2 blocks of the message, right? Unfortunately, but the good thing about this algorithm is that we only miss that, the corresponding message block and the neighborhood, but the rest would be all okay. So to make it kind of more understandable, let's say if you have any transmission bit error on 1 block, and suppose you are using AES, so we are going to miss 2 blocks of message, which means that we are going to miss 256 bits. Okay, so that 256 bits would be wrong, or we would get them incorrectly. This is quite common. For example, when you're streaming some videos online, and you're using, for example, CBC mode of encryption, and then sometimes the recipient would see some, noise, random noise on the video, just because, you know, we got 2 blocks wrong. So there would be some chops on the video. So audio would be a bit off for a second or so. Just the same amount depending on the quality of your video. The user might, you know, hear some noise, or the picture would stay still for a bit until, you know, depending on the encoder, video encoder that you have. So that would be, you know, the result that the user would see. If it is a document that you're sending, or if it is, let's say with the document, then 256 bits would be like a few characters, depending if it is using ASCII or non-ASCII code, that would be different. So unfortunately, we are going to miss some of the characters, or some characters would not make sense. For example, if it is Chinese, some words would be totally gone, or very different, would be printed incorrectly. If it is English ASCII code, so some characters would be missing from words. So that would be the effect. And if you are talking about a binary file, an executable file, for example, you know, so executable file is very sensitive to that. We might, you know, miss the entire file. So the entire file wouldn't work because some part of the execution file is incorrect. And, you know, that executable file wouldn't be useful anymore. Probably we have to download it again. So these are the effects of having, you know, some transmission bits. All right, if there's no questions, so let's have a break, a quick break, and we will come back in 10 minutes.